Next, I would like to introduce Alan Manlick from our USB team. So Alan will be able to share with you guys our USB PD extended power range, how to implement 240 watts with USB-C using our latest TIIC. Thanks, Alan. Go ahead. Yeah.
Is this on? Yep. Thank you. Thank you for having me here. Just got in last night. Wish I could spend more time here, but glad to be here and glad talking to you guys. Here to talk about USB Type-C PD specifically. Just quick show of hands. How many people here are familiar with USB Type-C or PD specifically? The TI people. Okay. So I kept this fairly high level, fairly generic in the sense of providing a little bit of background on both what is USB Type-C, how does it somewhat work to give you guys an idea of applications where it can fit, and then the new standards for within power delivery to be able to take up to even higher wattages, up to 240 watts to be delivered to applications. So today we're going to talk, again, like I said, a little bit of an overview of what Type-C is. But I want to get into applications, some high-level block diagrams of some typical applications that you could see. And then have at the end a slide on further reading more information where you can find information within our website. So Type-C, why it kind of came across to be able to get more data bandwidth, but also to be able to combine power, being able to provide power as a source or as a sink, to be able to take various types of data, whether it's combining in display port, Thunderbolt port, the old USB Type A and Type B connector, pulling that in. So video and audio, being able to pull all that into one connector now. And again, to be able to go from standard 5 volts, now all the way up to 48 volts and up to 5 amp power delivery. And again, on video, the new Thunderbolt 4 being able to get up to 40 gigabit per second data rate transfer through. So we support setting up the channels for doing all of that. We don't handle the actual USB data going back and forth. We handle setting up all the power paths, the voltage contracts, and then setting up the data paths for the USB data. So a lot of people ask, why would we move to USB Type-C from what we had before, whether it's barrel jack for power or USB traditionally Type A, Type B. So one of the main reasons is global mandates. Europe specifically, California in the United States, and in other countries are starting to adopt a common footprint, common connector, common interface to provide power and data to devices. So I don't know how you all are, but I have a junk drawer at work and a junk drawer at home that has all different kinds of power adapters, barrel plugs, Type A connectors, Type B, Mini B, Micro B, and you're always trying to dig through that to find the right one to connect through. So specifically in Europe, they acknowledge this is a massive problem leading to growth of landfills. Everybody's eventually throwing all this stuff away. They decided to work towards a mandate to standardize on a common interface. And that interface is USB Type-C. So that in turn is going to drive beyond just the PC notebook space and the phone space for Type-C charging, but into a lot of different areas. Anything that you traditionally saw a barrel jack to power something, you'll start seeing an adoption towards Type-C for that. And I'll show you some applications in coming slides for that. But that is one of the main drivers leading towards the need to do this outside of just data-driven PC notebook space. And again, we mentioned a single interface being able to provide power, video, data, all on a single line. And we'll get into the ability to be able to charge your device over that same connector or use it to provide power. So you could be a dual role power device as well. Again, we talked about the need to replace barrel jacks, to get rid of the myriad of different types of barrel jacks and all that. And again, a few applications, but industry-wide, again, outside of just PC notebook space, a lot of different applications are now driving this. We're seeing it in e-bikes, printers, you're seeing it in switches, power tools is a big one for all the different batteries being plugged in. You could just think of a lot of different types of applications that could use that. And again, especially now with the latest spec update being able to go up to 240 watts, that's a lot of power to be able to put across a cable and a connector like that. So I don't think there's not a whole lot out there that needs much more than 240 watts at this point in time. Any questions on applications or needs or anything to discuss? So I kind of mentioned there's two aspects to USB Type-C. There's the traditional USB Type-C specification that works at 5 volts up to 3 amps. Okay, very simple USB 2.0 kind of data transfer across, very simple. And then they came out with the USB PD spec that allows you to negotiate different voltages. So you can do 5 volts up to 20 volts on the traditional spec and up to 5 amp. And then the latest USB PD 3.1 spec will show allows you to go up to 48 volt 5 amp. And there's a communication mechanism that happens on the connector. I have a slide showing the connector interface. We use a couple pins on there to communicate back and forth and negotiate everything. So what I'm trying to show here is if it's a simple, very simple design where you don't need to negotiate anything higher than 5 volts, simple little, the real small little adapter chargers, 5 volt up to 3 amp. That's a very, very simple design. Don't need all the PD capability. But then you'll start seeing that if you're going to start going higher in voltage, higher in complexity, and tunneling video and all that through, then you're getting into the PD application. So on our website, we split the two. You can see USB Type-C only type applications, and then the more complex USB PD. And again, I mentioned the connector. A couple things to mention on this first, on the cabling, is if you notice, and you can kind of visualize, if you flip this around, you finally have a true reversible, flippable connector. So you look back at how like Type A worked, you couldn't flip it around. It was keyed so that you couldn't do that. You always had to kind of know how you were plugging it in. And they always keyed all the connectors, the Type B connectors, whether it was a mini, micro B, to do that. So here, they pretty much double the pins, but allow you to flip it around. So you have 4 pins for V-bus, and that's important for when we talk about higher current up to 5 amps, and then being able to put the voltage, be able to do that. But the CC pins are very important for negotiating the voltage and the current level. On the USB Type-C spec, 5 volt up to 3 amps, the current level is dictated by a pull-up resistor on the host side for how much current it's going to deliver up to. So you can either do legacy 900 milliamp, 500, 900 milliamp, 1.5 amp, or 3 amp. On the PD side, if they recognize that both sides are PD capable, power delivery capable, they actually talk on a communication medium between the two. And there's a whole communication protocol that'll go back and forth, and one side will show what its source capabilities are, and the sync side will say, great, I'll take 20 volt, 5 amp, right? And then that's how they negotiate back and forth on how that works. And that's done over the CC lines. And the reason why there's 2 of them, again, so it's reversible, and the communication happens only on one of the pins, and the other one ends up becoming power to your connector. Because a lot of times there'll be a PD chip inside the cable as well. So a couple reasons why you might need a cable that has a chip inside of it. If you, again, you have the Type-C spec, and then you go to the PD spec, that allows you to go up to 5 amps now. Anytime you want to go higher than the legacy 3 amp, you need to query the cable to see that the cable can handle that extra current, okay? And that happens, the power to the cable happens over the unused CC line, depending on how the cable was plugged in, and then the CC line queries the cable. So you can query the cable and you can query the far end, back and forth. And one more thing, as we talk about the new PD spec, the PD 3.1 spec, to be able to go up to 48 volts, so anything above 20 volts, you have to query the cable and make sure that it is PD 3.1 or EPR capable. So again, that's all for safety, so you don't damage anything on either side of the system. But that happens through the CC lines. Very important to the back end of the USB system working. The other lines like the TX plus and minus, RX plus and minus, those are your high-speed data lines for USB that are running through. And again, we handle the muxes on which path it's going to be running through and how many lanes are open, depending if you're going all the way up to the 40 gigabit per second. Again, any questions on the connector by itself? Again, I just thought I would show this to kind of show where, yes, go ahead. Sorry, so everybody can hear.
Can the cable be plugged in incorrectly, like one side's up and the other side's down?
Correct. So once you plug in, we automatically will know how it's oriented by the CC lines. So then it'll handle the muxes accordingly to know how to flip around. So you know automatically which side is, if it's connected one side up or down. And in some tools, and we actually have over here an example of a tool that we bought to be able to monitor voltages and current going through the USB cable and to be able to act as a sync so we can pick different voltage contracts. That one, for example, doesn't handle the flip very well. And you have to have the cable plugged in a certain way. But they should have handled that in there. But you know automatically, you get a flip event knowing that it's a inverted. And through our registers and through our GUI, you can actually see is the cable right side up or upside down. Yeah. Good question. So again, when do you need PD? Anytime you want to go above 5 volts, automatically you're going to need power delivery. So again, you'll use the CC as a communication medium. Anytime you want to do video processing through and you're going to pass through all that, whether it's Thunderbolt, DisplayPort, HDMI, whatever you're going to be tunneling through, or even PCI Express. And then a point I didn't hit on before, and another one of the key benefits that you have for USB Type-C, PD specifically, is the ability to do power roll and data roll swapping. And that power roll and data roll are not the same. So if you think of legacy USB Type-A, that the rectangular large connector you had that typically came off your old mouse and you plugged into your laptop, that was one-way host and device. 5 volts came through, the laptop provided 5 volts came through. Now in Type-C, either side can be host or device. Either side could be power or controller of the data, and you can flip dynamically, depending on what the need is. That's a very good feature. So if you think of your Type-C port on your laptop, if you plug in, you can plug in a mouse to it or a thumb drive, a Type-C thumb drive. Your host, your laptop is the data roll host, and it's also the power. You plug in a dock, it'll flip around. It'll be a power sync, so you can charge the battery from the dock, and then it'll still be maybe the data roll host. But dynamically, depending on the application, you can set it up to which way you prefer, or if anything happens real time under EC or embedded controller control, you can dynamically change. Any questions on that? Because that is fairly different compared to what you had previously and a little more dynamic.
Can you support a use case like just need 5 volts and audio support? I'm talking about what if I have an application just only need 5 volts and audio data? Does it
need a PD controller for that?
If the audio is going through the D plus, D minus to traditional, no. But if you're tunneling it through the high speed lines, then yes. But probably not. I don't know, SK, I don't know if you know.
I believe most of the audio actually went to the data D plus D minus
Correct. That'd be the legacy.
legacy. So actually you are pulling both CC1 and CC2 to RA.
Which, thank you for the question, because it actually pointed a couple pins I didn't mention before. So your traditional USB like 2.0 lines are the D plus and D minus. And audio accessory can tunnel through that. And that's typically how it'd be done. But if you're doing something much more advanced, part of a laptop, going to a dock, it would typically be done through PD. But if that's all you were doing is an audio accessory and 5 volt or less, I think it can be done straight through that. And again, the PD or the controller, the Type-C controller, does nothing with the data. We're just passing it through. So we're not in the middle of that at all. Thanks for the question. Any other questions? Again, I just thought I'd quick summarize the Type-C spec by itself. Again, 5 volt up to 3 amp, so 15 watt solutions. If you think of those little phone chargers and that we all had, that were the small little ones, those were typically 15 watt chargers, right? No negotiating, again, of different voltages to optimize charging of, say, your phone or whatever battery pack, or provide power beyond 5 volt, 3 amp. And again, the current level is up to 3 amp. It's negotiated by a pull-up that's programmable in the device on the host side. So on the CC line, the host side has a pull-up resistor that you program, and then the device side has a fixed 5.1K pull-down resistor. That voltage divider between the two dictates what the current level is going to be, and both sides can read that and know and agree on that current level. Again, 500, 900 milliamp, 1.5 amp, and up to 3 amp. Then when the PD spec came out, the main one being USB 3.0, configurable up to 20 volts. The standard contracts are either, you always have to have a 5 volt contract for legacy reasons, 5 volt, 9 volt, 15 volt, 20 volt. An optional 12 volt is pretty typical to replace a lot of barrel jacks, and battery applications will run, say, at 12 volt. So that's an optional one you can put in. I'll show in a coming slide programmable rails that you can program and agree on anything in between, but these are standard fixed rails. And again, up to 5 amp. The 5 volt, 9 volt, 15 volt are 3 amp max. Only the 20 volt can go up to 5 amp. And again, to get to the 5 amp, you have to have a cable that's capable of 5 amp. So again, you read the cable and it'll say, give me cable capabilities. They'll come back and it'll compare that it can do 5 amp. If not, it'll limit it at 3 amp for a safety reason. So again, up to 100 watt on USB PD 3.0. And then the new USB PD 3.1 can go up to 48 volt. So it adds in standard fixed voltages of 28 volt, 36 volt, and 48 volt. And again, up to 5 amp. And again, the cable has to support it. We have examples of EPR cable over here as well. We can show that afterwards at the next break. Different types of applications that may need different levels of power and different types of solutions, again, just to kind of show. Again, very simple devices for the Type-C by itself, little thumb drives, maybe a mouse, maybe something that it's not wireless, that's going to be plugged in and connected. Up to 100 watts, a lot of wall outlets that have the Type-C built in, or little adapters for that. Currently, PC notebook and a lot of these are starting to work more into the EPR as well, and especially gaming laptops. But monitors, same as well. You might see monitors coming out that'll go up to 48 volt, 240 watt as well. Any questions on applications? And again, as I mentioned before, if you think about the need to do barrel jack replacement or standardizing on a certain specific connector and cable assembly, you can start thinking through anything that you see at home or around the office that has a little barrel jack that's 240 watt or less. You're going to start seeing a migration to this over time, especially starting in Europe, starting now, and you're going to start seeing other countries and people following suit onto that. I mentioned a few minutes ago on the variable voltage within. So when I talk USB PD 3.0, that 5 volt up to 20 volt is called SPR, standard power range. In that range, or within SPR, again, I mentioned 5 volt, 9 volt, 15 volt, 20 volt. Then you can also do what's called PPS, Programmable Power Supply Solutions. They're in 20 millivolt steps. So you can think about it when you're working with a battery charger, you're on a charger side, you're going to want to negotiate for power efficiency reasons. The closer you can keep your input to what you're charging your battery to, and as you're charging your battery up, you slowly increase your input voltage or your negotiated contract, so you don't have a big drop across your power stage. So you can start going up in 20 millivolt steps. Very key for that. In EPR, that added the new voltages all the way up to 48. To come up with a different name for it, they call it AVS, for adjustable voltage supply. It's very similar, but it's in 100 millivolt steps. Okay. And again, as I mentioned, the fixed voltages that are standardly implemented, you can do 28 volt, you can have 36 volt, and 48 volt. If you do 48 volt, you're typically adding, if you do 48, you're typically adding 28 and 36 as well. So when you do the higher one, the lesser ones come along. And then that way both sides can negotiate as optimal as needed. So I mentioned getting into EPR, being that we're now dealing with higher voltages, higher power, there's a different entry sequence on that CC line, that communication to get in. And I'll show you a CC log of what some of that communication looks like in the next slide. But for safety reasons, there's an entry sequence to get into EPR now, so you don't erroneously try to set your laptop at 48 volts and it's not capable and you blow your expensive laptop up, right? That would be really bad. And then once you're in, being that you are now transferring higher voltages, not high voltages, but higher voltages across the cable coming in, there's a keep alive mechanism to make sure you stay in there, that both sides are in agreement. So again, I mentioned this 2-3 times. One of the first things you do is you query the cable. Are you EPR capable? If not, you don't even attempt it, right? Both sides would agree to that. The next thing that is done typically is you establish a SPR contract first. So you establish either a 5 volt, 9 volt, up to 20 volt contract to make sure you're communicating and you're established in both sides on agreed upon voltage level. Then the next thing is the sync would send a command to say, enter EPR mode. I want to go into EPR mode. And then the source would do the same. So both sides then agree that they're going to go into EPR mode. And then at that point, the source or the sync then will request, it'll know what the source capabilities are, and it'll pick a voltage in EPR to go to for that. And then you establish the contract. So the sync will say, tell me your EPR capabilities, 28 volt, 36 volt, 48 volt, or whatever AVS voltage they're in 100 millivolt steps, and they'll come back and they'll pick a value and they'll negotiate that value. So there's a several step process to get into EPR mode, and both will be set and working at whatever that higher voltage is. And again, once you're in, the sync side, the one receiving the power, will send a keep alive message, typically every 375 milliseconds, could be roughly 250 to 500 milliseconds. Excuse me. And then the source verifies that keep alive, and if not, they'll terminate that contract if If the source doesn't get that keep alive within, I think the spec is higher than that 500, it gives it a little bit extra time, then it'll terminate the contract and open a power path. This is one of the tools that captures and decodes all the traffic on the CC line going back and forth. But as I mentioned, it's just kind of showing the various steps here going through and to keep alive. And it's all the information decoded. So step one, discover identity. And I guess I didn't mention this before. A little bit extra terminology to know when you're talking about USB PD. SOP is the far end device that you're talking to. Say you're a laptop talking to a dock. The SOP would be the device on the other end, the dock. SOP prime is the cable. There's actually an SOP double prime for the other end of the cable. You could be talking either side of the cable. But in this case, we're discovering the identity of the cable, the SOP prime. Just in case you saw that, just want to kind of point that out. And then what it's coming back is, this is all the information that's coming back, and EPR mode capable, yes. So then with that, both sides know now they can move forward with the negotiation. Any questions on that? I kind of covered quite a bit and throwing a lot of three-letter acronyms out there, but to kind of get into a few application diagrams that'll be in the next couple slides, just high-level diagrams. I wanted to kind of talk through, again, part of the purpose of today was to give you a background into Type-C PD, and then specifically some of the new EPR. Our chips, not many chips from a digital and a controller point of view and a communication point of view can handle voltages up to 48 volt. So our chips now currently can handle up to 20 volts, actually up to almost 28 from a safety point of view, but we handle the traditional contracts up to 20 volt. So to be able to connect this to a system that's going to negotiate and provide power and talk through up to 48 volts, there's some extra circuitry now that's needed externally that on a simpler non-EPR was not needed. And I kind of highlight that here, and I'll cover from a high level what this circuit is. In future, in coming months, we'll have a chip that basically incorporates this whole block diagram on the left into it. We're going to incorporate that as a companion chip next to it to make it far easier to design in. So basically, what are we doing here with this circuit without getting too much into circuit analysis? This lightish greenish color here is basically a voltage divider scaling circuit that allows us to scale down the V-bus voltage from 48 volts to something 20 volts or less. So it's a divider network that when you're at 48 volts, you're going to be at 20 volts coming into our part. So we know what the divide ratio is going to be, and we handle that accordingly. So fairly simple. There's some FETs here, and what they do is allow for internal power path to still be providing power out to the connector. Say you have a 5 volt internal power path, and as I mentioned, every device needs to be able to support 5 volts natively by default right off the bat. So our devices have a internal switch, and let's say on the 5 volt side, we want to be able to bring that through. I can't bring it through the voltage divider network, so we provide a path to be able to bring that through out the V-bus here. Don't want to get too much into the details, but that's one of the main reasons for that circuit that's needed. The circuit in the purplish here on the left, it's actually being replaced. It's a comparator. So what we do is we guarantee that we're always running safe. Now that we're dealing with higher voltages and we know that the max voltage on our part is 20 volts, if something goes wrong or due to power up and the power supply on one end is still ramping down, because sometimes they take quite a bit of time to ramp down, and let's say it's started at 48 and it's sitting at 40 volts. We don't want to bring that into our part, right? That would be bad. So the comparator would automatically engage the divide network to keep our chip safe. So it's a safety circuit to keep over-voltaging devices. One of the key things to think about when you're using it, and you'll come through and you'll see the connector for the Type-C connector and the cable, it's really, really small. And one of the things, if the connector starts getting broken or people are wiggling it back and forth side to side, as you see how narrow the pins are, you got to make sure that you don't short one pin to another through the connector. And if I go back here, you can see that you could easily short, say, V-bus to an adjacent pin from that. So we call protection devices for short to V-bus to keep that from happening so that we self-protect ourselves. So there's some circuitry we put on there to keep those pins from getting exposed to 48 volts. Again, all part of our reference designs that we'll give out and share with you. And again, all will be part internally on this device here when we come out with that. So Type-C originally started mainly from a mindset of PC notebook, going into docking, monitors. I'll start from there, and then we'll work towards, like we said, industrial, could be e-bike, could be all that kind of stuff. So again, just tried to provide a little bit of mindset of what a typical PC notebook could look like. A few things just to kind of mention. Again, the PD controller, working through whether it's an internal power path or if you're going all the way up to 48 volts, definitely going to be external power path or what we call eFuse. Could be providing power. So most of the time PC notebook might only be providing 5 volt out, but could take up to 20 volts up to 48 volts. Say if you're going to be the new EPR spec for better charging of higher end gaming type notebooks. Could have a battery charger controller, so if you're running in as a sink up to 48 volt, that'll feed into here and then charge the batteries. Again, the EPR protection circuit we're showing for protecting the CC lines, the SBU lines for short to V-bus. Again, in a PC notebook, might have or in a monitor or dock, might have a Thunderbolt controller. EC for external controller for communicating with us, putting us in different modes, telling us what to do, controlling us on power up. I tried showing, and I think you guys are going to get all these slides, but I tried showing, even in the Type-C spec and from the USB on, there's been a myriad of different types of cables. And somebody asked me earlier, what happens if they plug the wrong version of the cable in? Meaning that as you go into EPR, it needs to be an EPR capable cable. If you want to go to 5 amps, needs to be a cable capable of 5 amp. The good news is if it's not and you plug in the wrong one, you just won't get that optimal charging or you won't get that power through. Or if it's a legacy PD or non-PD, just Type-C only, where all you're really bringing over is V-bus, ground, the CC lines, and the D+, D-, and no other communications, then you just won't get all those other capabilities. So somewhat flip-flopped or opposite of the host system, a notebook, is the dock or the monitor, where now you may be syncing up to, say, 5 volts, but typically you're going to be providing power to be able to go charge, say, a notebook, laptop. A lot of the rest of the system is fairly similar, but that's one of the main differences. So I don't show the connections here, but between the DC to DC converter on the last slide, this slide, and the next slides, and the PD controller, we actually control and talk to the DC converter or the charger for what is the optimal voltage. After we know what contract we want to establish, then we enable that through the DC to DC converter. And then once that voltage is at its safe value, then there's a negotiation process there where we send power good, basically PS ready, power supply ready. But that happens, there's I squared C communication between the two to make that happen. And again, the last block diagram that I show is not so much on the PC notebook space, but it could be from a charger point of view, but basically anything like your power tool, battery, your e-bike, anything that you want to do, true bidirectional. So your battery for your power tool, you may be providing power from the tool up to a tool, or you might be plugging it in to be charged, right? So it could either be providing power or syncing or charging. So again, showing now up to 48 volt bidirectional, either way, could be either way, more complicated design. And again, I do on this one show the I2C, but we talk back and forth to the charger. So we have various devices within TI that could be providing power in the, to the far end device, or it could be receiving power. Now, how you set that up is through I2C commands and enabling all that, and what voltage levels and what current limit levels and all that. All that is handled by the PD controller. Again, almost done here, but any questions before I kind of cover this? Get hold on a second so everybody can hear.
May I ask, like, from the EPR point of view, right? How do the system know the cable is can deliver up to like 5 amp current? Because some of the cable, the core, like some of the one which is very low quality type of cables, maybe only have 3 cores inside the cable, and then you quickly burn out the wires straight away. So in the system, how do they detect these kind of things?
Right, so good question. So to be an EPR capable cable, it needs to be able to handle up to 240 watts by its nature. It needs to be able to handle up to 48 volts within the cable and the connector itself, no issues, any arcing, anything like that. And the wires for the V-bus and ground need to be able to handle 5 amp. Actually, I think a little bit above 5 amp, but just say 5 amps. So whoever makes a cable and they claim EPR capable and they provide the details within the cable, the chip in the cable, again, there's a little chip that gets powered over the unused CC line. When they check that box that it's EPR capable, they are guaranteeing that it'll be able to work at up to 48 volts and 5 amp passing through that cable with no issue. Oh, yeah, sorry.
The way they did it is quite similar like what Apple did it right now. The Apple cable, Firewire.
Right. Okay. Same with when you get cables. Again, when you want to use up to 5 amp in a non-EPR, say up 20 volt 5 amp, same thing. If a vendor of the cable puts in there that is up to 5 amp capable, that cable has to be able to handle 5 amps. I'm not saying everybody always is honest about that, but that's the USB-IF interface forums mandate. Okay. Any other questions? Great questions, by the way. Okay. So at the end, I just provided a few links where you can find more information on our website. Just go into our website, go into the USB PD spot on our website. There's a myriad of different videos. We're updating videos. We're showing one here that we shot in a lab, but we're going to get the TI Studios to shoot a couple other videos that we'll post online as well.
I have one question, and I'm not an expert at USB at all, so
You can be.
Forgive me, it's a really stupid question, but so with the new USB 3.1 or whatever,
Yep.
what's going to happen with older flavors of USB? Is that maybe a dumb question?
You
Are we-
mean like Type A, Type B?
Right, all of these.
Okay, so there's still Type A stuff out there. You can still get a Type A to Type C cable. But I think over time, eventually, you're going to see that wane down. You're starting to see memory sticks now that are Type C memory sticks that can plug in. Takes a little bit of time because you got to have the ecosystem of devices out there. Same with EPR. EPR got announced, probably about over a year ago now, year and a half, 2 years ago. The first products, we got a handful out there now in various applications, monitors, different things, notebooks. As more comes out, it's going to proliferate faster. And then once that proliferation happens, you're going to see the older cables start going away. But there's a legacy that's got to happen too, right? To be brutally honest. If you had an old Type A thumb drive, you kind of want that for a while. So I think that's still going to stick around for the foreseeable future, just from a legacy point of view.
Thank you.
And again, that just happens through the D+, D- simple system. So the one connector can handle all of it. Got a question back here? Yep.
Hello, I'm Teck Wat from TPV. Just now I saw a slide that you show Thunderbolt cable, you require PD controller. Why is it so?
Sorry, I didn't quite pick that up.
You show a slide with the why PD controller is required.
For Thunderbolt?
Yes, why is it required?
So Thunderbolt 4 needs a Thunderbolt 4 cable. A lot of it has to do with the speed because you're going much, much faster. Need to query that capable of that. So there's cables for Thunderbolt, and it guarantees that. Hold on a second, I went too far. And it guarantees it has all the lanes. Not every cable has to have all the wires running through it either, right? But a Thunderbolt 4 is gonna have all the TX, RX, and all those wires guaranteed to be running through it. SK, I don't know if you have
So
anything.
you
you
mean
wanna add.
only the PD controller is able to do the query that all the lines are there?
The
PD controller mainly is to communicate what's the voltage and current requirement.
Yeah, the PD controller is the only one that can query the cable because it's another PD chip inside the cable. Just like what's in your laptop or what's in your dock or monitor on the other end of that cable, there's one of those chips. Smaller, simpler, doesn't need to do as much, but there's one of those inside the cable as well. Not always. Only if you need to do more advanced stuff, then there's one in the cable. Yeah.
Thanks.
But the Thunderbolt is for the Thunderbolt 4 for the higher speed, and as things keep progressing. Is there another question? Good questions. Oh, we got one back here. Yep.
Hello? Oh, okay. What exactly is like the price difference between, say, using a barrel jack and implementing USB PD in a project that would require like 200-ish watts?
Oh, that's a good question. I would say implementation cost, because you're going to need a PD chip and all of that, will probably be higher. But your back-end costs of all the throwaway and everything you're seeing will go away. But there is more to it, and the safety and the guarantee that you're doing it right. There's a little more to it. Actual price difference, I'm not sure. That's hard to quantify because a lot of it comes to what level, you're fully implementing. Are you? That's hard to tell, but there will be more to pay for the PD chip. You're going to talk to the power supply to be able to negotiate. You do get flexibility now because you get to negotiate any different voltage that you you want. Your system can be so much more dynamic. You can reuse across all different platforms now. Yeah. Got one more in the back.
Is there any mandate with regards to the length or the distance of the cable for USB Type-C? So, like, is there a minimum or maximum length that it can support?
Yeah, I don't have that data off the top of my head. There's typically cables come in certain sizes, and it more so comes across with I guess let me take a step back. Are you talking about like making your own custom cables or just ones you can buy? Because if the ones you can buy are already predefined, already guaranteed to work. So if you're talking like EPR cable, 48 volt up to 5 amp, they're already factoring that in, right? The wire size for the voltage drop. So the step back once again on that is the USB PD spec defines a upper and a lower limit for voltage across, right? And that factors in across the cable. So from host side to device side, that's being used to get the power. So at 5 volt, say it's plus or minus 10%. Let's say it can go 5.5 down to minus 5%, say 4.75 volts, right? So you have to guarantee that you can still be at above 4.75 on the far end device. So the cables are designed for that. If you make your own custom cable and you're going to go 20 feet long, you'd have to guarantee that you don't drop more than X in voltage across that. More of a voltage drop issue.
Yeah, I would like to know for the USB cable, right, the 3.1, there's two far end, right? Does the PD chips applies to both sides or is it one side?
All right, sorry, say that again, from the cable or from
For the cable, USB cable itself?
Most of the time in reality, there's only, you're asking if there's a PD chip
Yes.
on both sides of the cable?
Yes.
Rarely. It's usually just one side.
Okay, thanks.
And then you can query, both sides could query.
Yeah, because why I ask this question is because if the cable is too long, and then there will be a significant difference from each side of the query. So I thought it might implies that we need to have two. Yeah, but of course it will bring up the cost. Yeah.
From the query or from the voltage drop across?
Yeah, and the voltage across. Because
Yeah, so
yeah.
both sides are set to handle discretely themselves the over voltage or under voltage condition, or same with current. So if on the far end device you have something sitting out there and you have a 2 meter cable and you're dropping too much across and you go below the minimum threshold, it'll open its power path for safety reasons.
Okay, thank you.
Yeah, it doesn't, that itself doesn't have anything to do with the chip inside the cable. That's just the IR drop, the voltage drop.
Yeah, I got it. Thanks.
No, thank you.
Hello, Mark. I have a question for you. Can you jump to the page that I saw you have a block diagrams showing a connection, I2C connections to the Thunderbolt? Yep, here. So I saw there's a I2C port to be labeled as a TBT. I guess this is the stand for Thunderbolt, right? So may I know what this connection for? This I2C.
The Thunderbolt?
Yes.
Yeah, that's for if you have a Thunderbolt controller, say an Intel Goshen Ridge or something, right? That's handling the USB. It's basically like a big USB MUX as well. And that's for handling Thunderbolt muxing and all that through that controller. So the actual high-speed data lines run through that chip, and we're controlling the MUX on what to do.
So it means through the CC communication, so enter to antenna modes that request for certain, for example, video resolution be 2K, 4K. So it would need certain settings on the TBT, right?
That's a good point. So part of my high level, I didn't dive a little bit deeper into that topic. So we got a few minutes, I hope. So what happens, so I talked about how you handle a power negotiation, that it sends like, here's my source capability in a sync. It'll say like, I can do 5 volt, 9 volt, 15 volt, 20 volt at these currents. The sync side will say, great, I'll take this one. Part of the process as well for setting up the video tunneling and all that, it'll start saying, okay, what are your capabilities? What do you, excuse me, what are your capabilities? And it'll say, I can do these modes. I can do Intel mode. I can do all these. And from there, I can do DisplayPort. I can do Thunderbolt. I can do USB 4, whatever. The highest capable medium that is agreed on both sides is picked first. And then once that's picked, let's say you're doing Thunderbolt, then we'll go off and we'll communicate with the Thunderbolt controller, or we'll set up certain registers. There's a dedicated or a separate I2C lines going for us to that Thunderbolt controller. But that's negotiated over those CC lines on what video mechanism is going to get tunneled through the Type-C cable. And then we, like I said, we talk to the, in the case of a PC notebook, you typically won't see a Thunderbolt controller on there. It's usually embedded in the Intel processor, let's say, right? But we'll talk to the Intel processor for what's all going to be set up back and forth. On a monitor, if it's a Thunderbolt monitor or a Thunderbolt dock, there will typically be a Thunderbolt controller on there that we'll communicate with.
Okay, thanks for explaining that. So that means if using TI controllers, and TI would come out some sort of like templates or profiles that enable our chip to talk to the so-called the latest TBT devices from Intel?
Correct.
All right.
Correct.
Okay.
Yeah, we're set up to always be working closely with Intel and AMD for the latest chips that they're working on and coming out with, and we make sure we have capability to address those chips for the modes.
Okay, thanks.
And from a user point of view, all you're doing is setting up in a GUI. What do you want? I support, just my product will support DisplayPort, my product will support Thunderbolt, right? Whatever you're supporting, you just set it up from a GUI point of view, and then we handle the rest.
All right, thank you.
Thanks.
All right, any last questions? Okay. Yeah.
Okay, for the end product to put the USB-C 3.1 high power, I mean, do we need to go through specific certification tests, and also anybody is could be provide this specific test and roughly estimate of the cost of the test? Thank you.
Oh, there's a lot of questions there. I'll handle in the order that I know the answers on. Anytime you want to put the USB logo on there, you have to go through compliance, because you need to guarantee and show that you comply with the USB spec, right? So if you're talking non-PD, just whatever it is, even if you're PD, you have to go through those compliance specs. Then you can put the USB compliant, and now you're guaranteeing with whatever devices you're going to connect with, so you can use all the off-the-shelf cables and all that, that everything will work together. As far as cost for that, I don't know. That one I don't know. I'm not sure. I don't know if any of the apps people, FAUs, have any idea, but I'm not sure. I know we go through it and we pay. I just don't know what that is.
USB.org, and then they have a test house, specific test house, like Eden Lab, GRL, like Croy. There's a few test house. So you have to contact all these test house, and what is the requirement, how long it take, and how much it costs. So actually this one you have to go to their appointed test house, and then there are certain equipment and certain test parameter that they will perform, depending on what is your product requirement and
But
specifications.
For an actual dollar amount, I don't know what that is.
So all these things probably you have to contact them. I mean, one of the most famous one actually is Eden Lab, but I don't think it's actually in Singapore. It will be in Taiwan, China, and then GRL also in Taiwan. So GRL actually have some office in Singapore. You can contact them also. Yeah.
Right. Yep. I think we are about time. So we do have another break later. So later you can catch up with Alan separately. Thanks everyone for the participation on this USB PD.